All right. Now, in this case, module 4, we are going to exercise the nonlinear response history analysis of structures using EEUQ. To do this, let's start by just walking through the module, this file that kind of describes step by step the process that we're going to do and describes the context of the problem that we are going to do response history analysis on. And then we're going to work on kind of solving this module for the MCE ground motion intensity, and then you will have the opportunity to solve it on your own for the DBE analysis, and then have be able to compare the results here. If you have also worked on module 3, you will be able to compare the results from the nonlinear response history analysis for the same structure, but now with the results you had there, which were nonlinear static or pushover analysis, and kind of seeing what capacity they are similar or different. So let's start walking through the module here. The structure of interest is, again, the same structure as module 3, 4-bay, 4-story special steel moment frame that has reduced beam section connections from the beams to the columns, right, to ensure nonlinear response of the beams first and the columns. You have that building. The building is a perimeter frame, so most of all of these internal columns here don't have moment resistant connections. So in theory, they won't take any lateral force. Most of the lateral force would go on the perimeter frames in the east-west direction at the top, at the bottom, and the north-south directions on the left and the right. And this is how those frames look like in terms of east-west, in east-west direction. We have already provided the OpenCE Stickle model of this frame that's described here on this schematic. This is the name of the file. It's in the starter code package. That includes all the loading, all the loading and all the definition of the model. There is nothing that you need to change inside this model. And if you want more details about what the model looks like, you can look at the video and the descriptions in module 3 that deals with the same type, the same structure, the same model. The first mode period, the fundamental period of this structure is 1.12 seconds. Now, for this module, we're going to, the objective is to do response history analysis. So now we want to do dynamic analysis, where instead of pushing the building monotonically like we have done with the pushover, we're going to impose a ground displacement, and actually a ground displacement history, right? So we will be like moving the ground, following a ground motion, and that will induce vibrations and deformations in the structure that will, because of the intensity of the ground motion we're going to use, will certainly produce nonlinear response. So for that, we need to follow those steps that are here. We need to specify the number of samples. We're going to do 11 ground motion analysis, so we're going to do 11 samples. In this case, we're going to keep the structure constant. So we are going to ignore the uncertainty, the modeling parameters, and we are only going to consider the record-to-record variability, or in more plain language, the uncertainty in the ground motion, not the uncertainty in the structure. Theoretically, and in a more robust analysis, you need to consider both. And of course, you probably need to consider more than only 11 ground motions. That's a very limited sample to consider the big uncertainty that one can, that any place have on what type of ground motions could happen. Then we'll load the OpenCE model, and we'll do some of this, all of this directly on EEUQ. We'll select the ground motions, and then we will run the analysis. We could do that locally, like running in our machine, or we can also do it in the computational resources available to us through the SimCenter tools on DesignSafe. And then finally, we're going to take all of those results out and look at them, right? Review them and see what is the distribution of the drift responses, and if those drifts are aligned with what we are, how it compares to the performance of the building that if we have solved module 3 that we think that we have already some idea about. And then we will plot all of those results and compare those results against each other, the distribution of the drift along the height and the distribution of the peak floor acceleration along the height of the building. So let's do this. So let's start here by opening EEUQ. So you need to download EEUQ. First, that would be a zip file, most likely if you're a Windows user, and then you unzip it, and then you find here executable EEUQ. I would suggest you run it as administrator. And let's make sure I am sharing what I want to share. So let's share EEUQ. There you go. So now we are in EEUQ here. So for EEUQ, we're going to do forward propagation. We're going to do 11 samples. The general information we don't need it at this point because we're going to provide the model. The simulation is an OpenSys model. The input script that we are interested in, it's provided in the starter code. So we have our OpenSys model here. We define it. The response modes are important, and it's here we need to manually tell the analysis what is the node we care about on each floor, right? So for this, it's instrumental to kind of go back to the module prompt and then say what are the node that I'm going to focus on. So you basically choose a column line. I would recommend we choose any of those work, but maybe one in the middle. 31, 32, 33, 34, 35 would be a good option, or the one on the left, 11, 12, 13, 14, 15. Any of those would work. So let's do 11, 12, 13, 14, 15. The model is 2D, so spatial dimensions 2, degree of freedom 3 per node, and let's assume a damping ratio of 0.05, a 5% damping ratio, since that's the damping ratio that the building codes and the ground motion spectrum and the building codes assume structures have. Then we're going to select ground motions, and that's in the event tab. So for selecting ground motions, we're going to do peer NGA records. We're going to use the design spectrum from ASCE 7, and then we are going to put here what's the SS and the S1 for our problem. The SS here for MCE is 1.5. according to the module prompt, and S1 is 0.6, if I'm not mistaken. We want 11 number of records, and we leave everything else as default. And you're welcome to kind of look more into it. Basically, all of these other conditions will kind of reduce the amount of candidate ground motions that work, but will make it theoretically more realistically, right? Like if you know that you're on a site, for example, where the main faults are, say, strike slip, you could tell EEUQ to only select ground motions that come from that type of fault. The same for magnitude. You could constrain the magnitude, distance, and type of soil where the recorded ground motions came from. You can also then here define how you want the ground motion components to be treated. Since we're doing a 2D analysis, the best is to say I want to treat each ground motion, each component of the ground motion as independent ground motion. What this is saying is every recorded ground motion has at least 3 directions, right? North, south, east, west, and vertical, right? So when you go to a seismic station or accelerometer station, you have those 3 sort of measurements. But the building we have here, we don't know in what direction the ground motion is going to come, right? So you could kind of, if you ignore the vertical, you still have 2 options, right? You still have 2 options, and you need to choose one direction to input to this 2D model, right? So there are a few options, right? You could use the sum of the square root of the sum of those 2 directions, of the sum of the squares of those 2 directions. You could use other definitions that kind of do a little more intricate versions of this rotation to get the what's called the ROD D100 or ROD D50 or the geomean. Or you can just take each direction as if it's individual and it's a different ground motion, and it could hit on one direction or the other direction. So we'll do that to simplify the problem since we have a 2D model. If we have a 3D model, then those rotation assumptions become a bit more important. Then we want to do ground motion scaling. So we want to minimize the mean square error between the ground motions that we select and the ground motion target that we have. And here we select the period when we want to enforce that error function, right? So in this case, the recommendation is that we select ground motions to fit between 0.2 and 1.5 times the period of the building. Our building has 1.12 seconds. So from 0.2 to 1.5, we're basically between 0.22 to 1.68, if I'm not mistaken. And then we can put some other numbers to anchor the calculation in the middle, right? So like 0.45, then 0.6, 0.8, 1, maybe 1.2, 1.1, and then here 1.4. And we're going to do the same weight everywhere. And then we hit select records. That will prompt us to log into the peer NGA database. This is a really good database of ground motions that have been collected around the world and have been processed and organized in a uniform manner, ready to use in nonlinear response history analysis of structures. If you don't have an account, you need to click this link that will open up the peer NGA database where you can log in, create your account, and with that access the ground motions. I already have an account, so I'm able to log in, and then that automatically would kind of get EEUQ to select ground motions. So here you can see kind of on this log plot how on the region around the 1.12 seconds we kind of get ground motions that are pretty similar from the target, which is this blue spectra, and each of the gray ones correspond to each of the ground motions that was selected, and scales, basically multiply by a scalar to get it closer to that target. And now that we have the ground motions, we move to the finite element model. We have an OpenSys finite element model, but then we want to do an analysis script that it's predefined, it's part of the input file. So in the starter code, we come here, we select the solver, and that will kind of basically just have an algorithm that will help us jump through convergence issues and test different solution methods to get to an effective solution. The outputs, the engineering demand parameters, we want standard earthquake outputs. Basically, for each floor, give me the peak interstory drift and the peak floor acceleration. Random variables, we don't have random variables because we are ignoring uncertainty in the material properties, only uncertainty in the ground motions is what we care about. And then with this, we can run the analysis. We have option to run it locally, an option to run it on the design safe high performance computer resources. Let's try to do it in design safe. If we do it in design safe, we need to create an account in design safe. First, we logged in. And when we logged in, it will try to connect us. You can see the program output down here, what's happening. It connected us. Here, we just need to define what's the job name. So we say EEUQ class. We require 1 node and 11 processes because we just have 11 analyses. So the best way would be to just run 11 analyses in parallel. And all of those would kind of run in the time that the longest one of all of the 11 take. And we could start selecting the maximum runtime we expect. This is a relatively small building, so with 20 minutes, we are fine. We submit the run. Okay. It was submitted, and then we can hit get from design safe to see all the jobs we have submitted. Right, in the different jobs we have submitted, there's you see the latest one here and the status. Right now it's tagging inputs. Now it's queued. You can see here how it's been. Now it's in the queue. And once so basically right now we are in the queue of many users sending jobs to design safe. While that's going, we could also run it locally. So we could just hit run here on the left, and that will be running the analysis locally. While it's running locally, we can also go and look into our temporary file where EEUQ is. So basically, you can go to your documents, normally pretty much the same location where you had the values or the local directories for QFM, but now look for EEUQ, typically documents, EEUQ, local working directory. And there, and let me show the screen to show you there. Here it is in documents, EEUQ, local working directory. You have a temporary sim center file, and that one basically has the 11 working directories that include the analysis of the same building on each of the different 11 ground motions. So you can go here and you see here is the model that is running through each of those ground motions, and is only running one of them. Although the way that EEUQ kind of works is that it copies all of them, but is only running one per working directory. So look here, and we have finished up the run, right? All of the 11 analyses have been ran. Let's look from design safe just to see what happened there. It's still queued. We can refresh the job. It's still queued. So in this case, since this is a really small structure, it was a lot faster to do it locally. But when you have a bigger structure and you're doing not only 11, but say 100 analysis, then it probably would be much more efficient to do it through design safe. All right, so this is the result. So basically for each of the stories, you get peak floor acceleration and peak floor displacement, and also a peak into story drift. You get a mean and standard deviation from those 11 numbers, right? You can kind of take the data values and export them as a table. So you can say save table and save that. Here you can save it. So for example, this is for the MCE. So you could take that and save it as MCE. Save. And that's it. So with that, we have finished the run for MCE. You could repeat this for DBE. Now let's look at the post-processing. For post-processing, we have prepared Google Colab that you could look at in your starter code. So if you come here, the module 4 in the starter code, you see this this notebook, right? And this is the file we just saved from EEUQ. So you can open this in Google Colab. You can open it up in Google Colab, and I'll show you. And then you make sure we are projecting. There we go. So it is in Google Colab. What this folder basically does, or this notebook, then it's basically post-processing the results. So it has all the inputs from the building that are necessary, and then asks you to upload two things. The first thing, it asks you to upload the results from the table we just saved. So you can choose the table here. You go here and you choose the table. You choose the table, MCER. But then also ask you for a zip file. What is that zip file? Well, that zip file is a file that includes the information from this template directory. That's basically because that's basically you need that because you need the information of the ground motions. So for that, for plotting the outputs that are required for the module. So what you can do is that you go to the local directory, zip this template directory, and save it in in a place of you choosing and upload it here. So you choose it and upload that zip file, and then you can use this notebook to load those files in, and then load each of the ground motions and calculate the ground motion spectra for each of those target for each of those ground motions, and plot them together so that you can compare it a little bit better than using that log file that EEUQ presents. And then you can see the target spectra and also the spectra of all of the ground motions that were selected by EEUQ, selected and scaled by EEUQ automatically. Now, here, this folder also, or this notebook also helps you look at the results from the lateral response. So let's look at, you know, what was the target spectra in black, what's the mean spectra of the 11 ground motions you chose, and the 11 ground motion spectra themselves in gray, right? So you see that in between 0.2 and 1.5 times the fundamental period of the building, the mean spectra of all of the ground motions you have really resembles the target spectra, and you still capture some uncertainty around it, you know, which is a lot more realistic. Now, also in this latter part of the notebook, just helps you plot along the height what is the peak interstory drift and the peak floor acceleration, right? Again, in gray, it's each of the responses for each ground motion, and then you have in blue the mean and plus and minus 1 standard deviation. In summary here, for the MCE, this building has a maximum peak interstory drift of almost 5%. On average, or the median value is 2%. And the peak floor acceleration is the maximum is 125 G and the median is 0.9 G. Now you can compare these results with those that you got from the pushover analysis and repeat this analysis for the DBE and compare with the MCE and the pushover. And with that, you have a full picture of what's the nonlinear response of the building that could give you an idea of what could be the performance of this building subjected to earthquakes. I hope this is instructive and look forward to all your comments. Thank you so much.